Hello friends, welcome back. So this is the second video on geometrical optics, and here we will learn about refraction. So here we will first learn about the basics of refraction, then we will understand critical angle and total internal reflection. Then finally we will apply both these concepts to understand refraction at a spherical surface, and then we will derive the equation for refraction at a spherical surface. So let's get started. So let's understand refraction. So let's say we have a fish inside water, and above the water we have air, and in the air, let's say on a boat, there is an observer which is observing who is observing the fish. Now water is a transparent medium, and let's denote that it as M1, and so is air. So let's denote the medium air as M2. Now refraction is a phenomenon by virtue of which a light ray bends when it travels from one transparent medium to another transparent medium. This particular example, this fish will emit light rays in all directions. So one such light ray will go along this direction, and at the surface of separation of water and air, the light ray will bend and then it will reach the observer. So for the observer, it will appear as if light ray is coming from fish only, but that fish is not located at position A, but at position A dash. So for the observer standing on the boat, the apparent depth of the fish will be lower than the actual depth of the fish. Okay. Now we measure refraction by a metric which is called refractive index. Now every medium will have a refractive index. Now, so this water will also have a refractive index. So since water is mu1, so let's denote the refractive index of water as mu1. The air is medium 2, so let's say the refractive index of air is mu2. Now the relationship between the refractive index of water and air is given by this equation. So mu2 by mu1 is equal to v1 by v2 is equal to sin I by sin r, where v1 and v2 are the velocity of light in medium 1 and medium 2 respectively. Okay. Now for vacuum, the value of mu is equal to 1, and for air, the value of mu is more or less equal to 1. So for all practical purposes, the mu for air we will take as 1. So if we apply this equation in this particular example, what will be the value of mu2? So mu2 is the refractive index of air. So mu2 is equal to 1 divided by mu1, refractive index of water, is equal to sin I by sin r. Okay. Now here if we apply a little bit of geometry, then we'll figure out that mu, which is the refractive index of water, is equal to O divided by OA dash, where OA is the actual depth of fish and OA dash is the apparent depth of fish. Now let's understand critical angle. So when a ray of light goes from a more denser medium to a less denser medium, then the refracted ray bends away from the normal. Okay. Similarly, from a ray of light comes from a less denser medium to a more denser medium, the refracted ray bends towards the normal. Okay. So in this particular example, the ray of light going from the fish towards air, in this particular example, the refracted ray in the air will bend away from the normal. Okay, because water is denser than air. So let's say for a particular ray as shown here, the angle of incidence is I1, the corresponding angle of refraction is R1. If we increase the angle of incidence from 1 to I2, the corresponding angle of refraction will also increase to R2, where R2 is greater than R1. And this will go on till we achieve, the angle of refraction as 90 degree. So the corresponding angle of incidence for which the angle of refraction is 90 degree is called critical angle. So in this particular example, IC is the critical angle. Now, if the angle of incidence is more than the critical angle, then refraction does not occur. The entire light gets reflected the way as if the ray of light is hitting a plane mirror, and this phenomenon is called total internal reflection. Now let's apply the refractive index equation to get the critical angle. So for critical angle, if we apply the refractive index equation, we will have mu2. So in this particular case, mu2 is air. So mu2 for air is 1. So mu2 is equal to 1 divided by mu1. So mu1 is basically the refractive index of water. So divided by mu is equal to sin I by sin r. So is equal to sine of I. I is what? IC divided by r. So for I, for critical angle, r is 90 degree, so sine of 90 degree will be equal to 1. So basically, critical angle is defined as sine inverse of 1 by mu, which is 1 by the refractive index of the of water in this particular case. The concepts of critical angle and total internal reflection have many widespread uses. One such use is in the optical fibers, which are fibers made up of transparent glass or plastic, and they are used to transmit information between two places. They have application mainly in the telecom sector. So let's say we have a city A and we have a city B, and between these two cities information needs to be transmitted. So an optical fiber will be laid between these two cities, and information from city A will be passed through the fiber with the help of light ray. So a light ray will enter the fiber, and then the light ray will move inside the fiber, and finally the light ray will reach city B. Now the diameter of the fiber is deliberately kept very low, in the range of a micrometer. Now because of the small diameter of the fiber, the light going inside the fiber makes a nearly glancing incidence on the wall. Now because of this, the angle of incidence is greater than the critical angle, and hence total internal reflection takes place, and thus the light gets transmitted through the fiber, having multiple total internal reflections, and finally the light reaches the end B without any appreciable loss. So optical fibers provide a very efficient way to transmit information. So now we are going to look at refraction at a spherical surface. So the analysis here is very much similar to the analysis we did in the last video where we discussed the reflection at a spherical mirror. So here let's say we have this spherical object as denoted by this curve, and let's say the refractive index of the spherical object, which is made up of glass, is mu2, and outside the spherical object we have air, and let's say the or any other medium, and let's say the refractive index is mu1. And let's say we have this OI is the principal axis of the spherical object, an object O on the principal axis at a distance of OP from the spherical object. And so light from this object O will be emitted and will be refracted. So let's say OD is the incident ray and DI is the refracted ray, and let's say EC is the normal. So we will have angle of incidence as ODE. This I is the angle of incidence, and this R is the angle of refraction. Now the subsequent analysis is pretty straightforward. So let's first denote other angles. Let's say this angle DOP is alpha, angle DCP is beta, and these angles, this is the angle of refraction, and this angle is gamma. So if we see triangle DCI by the law of triangle, beta is equal to R plus gamma. Similarly, this angle EDO, I will be equal to beta plus alpha. Okay. Now then we apply our very famous refractive index equation. So in this particular case, it will be sin I by sin R is equal to mu2 by mu1. And here, please note that for our analysis, we'll assume that the point where the incident ray hits the spherical object, that point which is D, is very close to the pole. So in a way, the angle of incidence is alpha, R, and gamma. All these angles are very small, and for very small angles, let's say for a very small angle of incidence, sin can be just written as I. So if we do that, this equation will become mu1I is equal to mu2R. And if we replace the values of I and R from the above two equations, we'll have mu1 into alpha plus beta is equal to mu2 into beta minus gamma. Now alpha, beta and gamma are very small. So in this particular case, for very small alpha, we can write alpha as dP by PO. Now if you have doubt in this, then I would request you to watch my first video titled Mathematics and Physics. So there I have explained how to write values of very small angles. So here similarly beta will be what? dP by PC, and gamma will be what? dP by PI. So let's put these values over here, and now we have to apply our sign convention. So if you remember our last video on reflection at a spherical mirror, what did we discuss in the sign convention? First point was that all distances are measured from the pole. Okay. Second point was that the the direction of the angle of incidence, which is this direction, is considered positive, and the direction opposite to this direction is considered negative. So let's say here this OP, which is the object distance. Let's say the magnitude of the object distance is U. PI, this PI, which is the image distance. Let's say the magnitude of image distance is V, and PC, which is the radius. Let's say the magnitude is R. So if we apply the sign convention here in this equation, we will mu1 by PO. So PO or OP is U, and the direction is opposite to the direction of incident ray, right? So it will be minus U. So mu1 by minus U. PI is what? The magnitude is V, and the direction is in the direction of incident ray. So the value of PI will be plus V. PC will be what? PC, the magnitude will be R, and the direction is along the direction of incident ray. So the direction will be plus R. So if we apply these values with the proper sign convention here, we will get mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. Now this is the equation for refraction, or rather I should say this is the general equation for refraction at a spherical surface. So I will stop here. That's all I have in this video. In the next video, I will extend this concept to understand lenses. So thanks for watching. See you in the next video.